When solving second-order linear homogeneous differential equations in the form y double prime plus p of x times y prime plus q of x times y equals 0, it's important to know if two known solutions are linearly independent or linearly dependent. If we take a look at the theorem at the bottom of the page, if p and q are continuous functions and y1 and y2 are two linearly independent solutions to the homogeneous differential equation, then every solution is in the form of y equals c sub 1 times y sub 1 plus c sub 2 times y sub 2, meaning y equals c sub 1 times y sub 1 plus c sub 2 times y sub 2 is the general solution. If y sub 1 and y sub 2 are not linearly independent, meaning they are linearly dependent, then this is not true. And now let's discuss how we determine whether two given functions are linearly dependent or linearly independent. At the top of the page, if two functions y1 and y2 are linearly dependent, then there exists the constant a such that y sub 1 equals a times y sub 2, or y sub 1 divided by y sub 2 equals a constant a. If a is not a constant, then the two functions are linearly independent. As an example, let's consider the differential equation y double prime minus 2 x to the power of negative 2 y equals 0. Assume we know two solutions are y sub 1 equals x squared and y sub 2 equals 1 over x. Are the two functions linearly independent? If they are, then we can state the general solution. To determine this, we divide y1 by y2. We could also use y2 divided by y1, but in this case, y1 divided by y2 is x squared divided by 1 over x, which gives us x squared times x over 1, or x cubed. Of course, x cubed is not a constant, which indicates the two functions are linearly independent, and therefore the general solution to the given differential equation is y of x equals c sub 1 times x squared plus c sub 2 times 1 over x. And now let's get some additional practice on determining whether two given functions are linearly independent or linearly dependent. Here we're asked to determine whether the given functions are linearly independent or linearly dependent. For number 1, we have f of x equals e to the x and g of x equals e to the power of x plus 4. We can either divide f of x by g of x or g of x by f of x. I'm going to go ahead and divide f of x by g of x. And again, if we get a constant, the two functions are linearly dependent. If we don't get a constant, the two functions are linearly independent. This gives us e to the x divided by e to the power of x plus 4. Recall, when dividing the bases of the same, we subtract the exponents. This simplifies to e to the power of x minus the quantity x plus 4, which gives us e to the power of negative 4 over 1 over e to the 4th. And because e is a constant, this is also a constant, which indicates the two functions are linearly dependent. Number 2, we have f of x equals e to the x and g of x equals e to the power of 2x. Again, let's divide f of x by g of x and see if we get a constant. This gives us e to the x divided by e to the power of 2x. Simplifying, we have e to the power of x minus 2x, giving us e to the power of negative x over 1 over e to the x. And 1 divided by e to the x, or e to the power of negative x, is not a constant, and therefore f of x and g of x are linearly independent. And for the last example, we have f of x equals 2x squared plus 8x, and g of x equals x squared plus 4x. Again, let's divide f of x by g of x, which gives us the quantity 2x squared plus 8x divided by the quantity x squared plus 4x. Let's go and simplify by factoring. The greatest common factor in the numerator is 2x, giving us 2x times the quantity x plus 4. In the denominator, the greatest common factor is x, giving us x times the quantity x plus 4. Simplifying, x divided by x simplifies to 1, and so does x plus 4 divided by itself. Simplifying, we just have the constant 2. Because f of x divided by g of x is equal to a constant, f of x and g of x are linearly dependent. I hope you found this helpful.